Mostly this morning is just trying to take this 30,000 foot view of the C++ language. So there's a couple of terms you need to understand. One is scope. Scope is everything that's included between a pair of curly braces, open brace and closed brace. That has very specific semantic meaning in C++. When the thread of execution enters a scope, memory is allocated. Temporary scratch-pad memory is allocated for that scope. So, for example, when I call a function has curly braces, that scope, memory for that scope holds the calling arguments for the function. It holds any local data that I declare in the function, and it holds the results that are returned by the function. When my thread of execution leaves the function, that memory becomes invalid. It doesn't mean that it goes away. What it means is the next time I call a function, that same memory is going to be allocated to that next function, and everything that I put there in the first function gets overwritten. Bam! Becomes invalid. So this is an efficiency mechanism, a really nice mechanism for using memory resources efficiently. And because we use memory resources efficiently, it means that things run quickly because the smaller our footprint is, the fewer page faults we do, and page faulting is one of the slowest things a program can do. And if you don't understand what page faulting is, you will by mid-semester when we talk about threads. We'll talk about that sort of stuff a lot. So scope is a set of statements enclosed by curly braces, and there's function scopes and control scopes are executable scopes. There are scopes that are not executable, for which memory is not allocated. Namespace scopes, and class and struct scopes and enum scopes are declaration only. The namespace, class, struct, and enum scopes are compile time artifacts. Once the program is compiled, they're gone. They don't exist. They were used to compile to say, yes, you can access this, or here's where you go to get that. But once compilation done, they're gone. But function scopes and control scopes, the curly braces associated with a function or an if or a for or a while or something, those are runtime artifacts. When you enter a scope, you allocate memory. When you leave the scope, that memory becomes invalid. And C++ does a really nice thing. When you declare an instance of some type, some class, in a scope, when you leave that scope, guaranteed a destructor will be called that will deallocate the resources used by the class. So when you declare an instance, that class allocates resources, and when its destructor is called, it deallocates, and the C++ language guarantees that the destructor will be called when you leave the scope. So that scope-based resource management is very elegant, much more elegant than garbage collection. I'm not a big fan of garbage collection. You know, the C++ and Java garbage collectors work really well. They're well engineered, you know, but they have some funniness. And in my opinion, garbage collection is a solution looking for a problem. I'm not a fan of garbage collection. But anyway, you know, garbage collection was invented so that developers didn't have to handle pointers. So the language designers are saying to you, we language designers have to have pointers. You developers don't need pointers. They're dead wrong. A lot of the things I complain about in Java and C# are because of that, because of, and you know, I'm biased. You know, understand that I am very biased. I love C++. C# is fine. Java is fine. They're good languages. But I would prefer to write code in C++ any day of the week. For reasons I'll talk a little bit about today, and I'll continue to talk about the sun. You don't have to agree with me. It's okay. Okay? I am biased. All right? So, and I'm willing to stand up in the soapbox and pound on the table and stuff. So, but anyway, so understand scope and stack frame. So stack frame is just when I enter main, a stack frame is allocated to main to hold its data and stuff. When I call a function in main, another piece of stack memory is allocated, and mentally you can think of that as being, here's main stack frame and here's that function stack frame below it. And if that function calls another function, down below it is another stack frame. So the stack frame just describes the memory that's allocated, that scratchpad memory that's allocated to a scope. And it isn't just function scopes. When I enter a for loop, that scope and memory is allocated just for that for loop. Okay. There will be a help session tomorrow at 9 o'clock. And did I say this already? If there's overflow, so what happens is there's a big class, and we may have more than this room more people than will fit in this room. What happens, I'm not allowed to let people stand up and lean against the wall. The fire regulations say everybody in the room has to have a seat. And so what will happen is if the room overflows, I'll tell you can't, if you're standing up, you got to leave. But what I will do is if we overflow, I will start the help session at 9 and go till 10:30. And at 10:30, I'll kick everybody out and take the second wave of anybody that couldn't get in at 9. Now understand that if we don't overflow, there won't be a second wave. So don't say, oh, I'll just come at 10:30 because he's going to do a second. I'm not. I'll only do it if there's overflow. You need to have Visual Studio 2017, and you can get that from free from DreamSpark, or from you can just download. Clicking on this link will take you to the Community Edition. I'm running the Community Edition on most of my machines on this machine, and most of my machines. It works just fine for this class. We'll come back to this problem with dependencies sometime. We don't have time to talk about it this morning. I'm not going to talk about Project 1 this morning. I want to do a survey of the C++ language. I showed you last time a little diagram of the language evolution. That's what that link goes to. I showed you a getting started, and this is the wrong link. So if I'll fix that link. If you go up to Notes, Getting Started, here's what that link should point to. That this is a page just dedicated to C++, and it has a little more in it than the other link, and I will fix that other link. Nag, send me an email and remind me to fix that link on the Lecture 2 page. It goes to Getting Started. So, it just tells you some things you can look at early on, basic syntax and course summary, and the classes and class relationships and templates and stuff. These link to the same thing that these do in the notes, classes and templates. So let's take a quick look at the classes. So C++ was designed from the ground up to support value types. That is types that can be copied and assigned. You can't do that in C# and Java. You can assign handles, but that doesn't assign the instances. If you assign one handle to another, or copy a handle into another location, they both point to the same instance. In C++, C++ was designed to allow you to do copy and assignment of instances. So the stuff, if I point to something on the heap, I can make sure that what I copy is just not the pointers, but I copy the contents, so that when I'm done with that assignment or copy operation, I have two instances that, as soon as I've made the copy, they have the same state, but those states are independent. They all can go off on their own lives and have their own contents, which is not true of C# and Java. So a class has, I'm illustrated here, constructors and a destructor. Any function whose name is the same as the name of the class is a constructor. And its job is to allocate memory and initialize it. If you're used to programming in C, you've used malloc and free. Malloc gives you memory, but it doesn't initialize it. Your code has to go and initialize it. In C++, the designer of the class has written code in this function to initialize that memory. So the user of your class just declares it, and that memory the language guarantees that when you declare an instance of a class, it is initialized with a constructor, and when it goes out of scope, its resources are returned by the destructor. So this is a default constructor, which might be used to initialize elements of an array, be called repeatedly for each element of the array. This is a promotion constructor. It takes an instance of some other type and promotes it to an X type. If this was a string class, maybe I take a literal string. I have a constructor that takes a literal string, a quoted string, and builds a instance of the string class. So I'm promoting a literal string to that instance of a string class. This is a copy constructor. The default action when I pass by value and return by value is to invoke the copy constructor. And the copy constructor's job is to make a deep copy if deep copies, if you have non-primitive data. And it always has this kind of signature, x const x by reference. And the assignment operator always has this same signature, x by reference, const x by reference. And that allows me, I can define the contents of the copy. It's my job to define the contents of the copy constructor so copies happen correctly, and to define the contents of the assignment operator so assignments happen correctly. But nobody else, the users of my class, don't have to be concerned about that at all. They just use it, bang. And starting in lecture 4 and 5, I'm going to walk you through that in gory detail. We're going to see how every one of those functions is developed. So there's a lecture on what I call, there's 2 lectures on abstract data types. And I'm going to walk through every single one of these. There's a lot more than these. Every single one of the functions in the class. And I'll show you, here's how it's declared in a class. Here's how it's implemented in a CPP file, and here's how it's invoked in some application code. We're going to take method by method by method by method to make sure that you understand how all that works. And typically, unlike Java and C#, we declare methods in a class and we implement them in a separate file. C# and Java force you to put that code inline in the class. And I'm not a big fan of that. It makes it hard to understand what the class does. You look at it, what's the language supported by this class? I don't know, because all I see is code, lots of code, blah, 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 blah. But in C++, I can look at it and say, oh, that's what it does. There's this language. It's not quite as cut and dried as that, because in Java and C#, I can create an interface It does the same thing that this class does, okay? So in fairness, but there's one more thing I got to write in C++. By default, we tend to write these things that way, and that means that a user can really easily see how the class is used right off the bat. So classes. So class's job is to manage some data. In this case, I have a pointer to a string on a heap. And normally in a class, if I'm going to use a string, I would just make it a member of the class. I wouldn't put it on the heap. But this is just for illustration. The job of the class is to manage some data, and the data should not be accessible to anyone except member functions of the class. And so the class can make a strong guarantee about the integrity of that data because it's just the class methods that can interact with it. If the data is made public, anybody can come along and do any horrible thing to the data they want. Maybe you got something on the heap and they delete it, and then your method function, your member function calls on that pointer and throws a memory exception because it's no longer valid. Okay. So you don't want to make your data private. You don't want to make your data public. You want to make it private. There's lots of parts to that story, but so that's the basic idea of a class. And there are templates. This happens to be a little utility, a conversion utility. Here in a template, for reasons that I will begin to hint at later on this morning, the implementation code for the templates have to be in the header file. For non-template classes, we don't do that. We just put the class declaration in the header file, and we put the definitions in an implementation file. For templates, they have to be in the header file, and you will know why in gory detail by the time we're done with templates, but I'll say a little bit this morning that will hint at why we do that. But anyway, and templates allow us, so that the thing about templates is that they do their operations in terms of some unspecified parameter. And so that means that if I want to run, this happens to be a conversion utility that has a toString and fromString function. So I can take a double and create a string representation of the double, and I can accept a string representation of a double and turn it back into a double. And the same thing for an int, same thing for a complex, same thing for a string, And so without templates, I would have to write a class for ints, a separate class for doubles, a separate class for complexes, and it's open-ended. It will go on and on and on and on and on. Okay. I would have an obligation to write classes forever. Okay. But templates allow me to provide this template, a generic representation of that operation for whatever type I want to supply. And that does. Now, C++ templates are a little more powerful than C# and Java generics. The reason for that is C# and generics are runtime entities. Essentially a generic, underlying a generic is an object type that going into and out of this casting going on, runtime casting that's going on, to enforce that particular type. You can only put, if it's a container, you can only put widgets. If I construct a container typed on widgets, and I can only put a widget in, but it's really stored as objects, and there's casting back and forth. In C++, templates are resolved at compile time. And that means that my application declares an instance of a template with some type, and the compiler does that binding, no casting, just binds it. And what that means is that we can specialize that. We can define a specialization of that template. So here, if you don't find a specialization, use this generic template. But for this particular type, do this. For this other particular type, do this. So it allows us to tailor. Almost nothing can be written, piece of code can be written that'll operate with absolutely every single kind of type you could give it. So specialization allows us to really gracefully handle that, and you can't. C# and Java don't provide a mechanism for specialization. They can't because generics are really a runtime phenomenon. There is no compile time type type evaluation. Okay. So so why C++? Why not C# or Java? I have this in. I'm looking at the wrong one. So, there's something I want to look at before this. Hang on a minute. C versus C++. So, my assumption is that most of you are pretty comfortable with C. Maybe not everybody, but most of you are. So, I do a lot of comparison with C++ with Java and C#, but let's compare it to C. So what does C++ bring to the party over C? So C++ started out from C. Its first version was C++ with classes. It was named C++ with classes. I'm sorry, it was named C with classes. C with classes. Plus plus is the incrementing operator in C++. And so it was a joke. The name C++ was a joke. They said, oh, this is C++. Incremented, okay. So, and it stuck, the joke stuck. But anyway, C++ adds references to the language. In C, indirection is done with pointers only. And you use pointer syntax. You use for, to access an element of a struct, for example, you'd say dot. But if I want to access, if I have a pointer to the struct and I want to access it with an arrow. References are really pointers under the covers, but they use object syntax. So if we want to access something that is referenced through that underlying pointer, we use dot. So it's like interacting with an object, even though it's indirect. And it's, that's a little bit of syntactic sugar, not all that important, but it turns out that it's more important than it sounds like because of things we can do with functions and function signatures. Function overloading. So C doesn't have overloading, at least in the version of ANSI standard C that I use. C has been kind of growing off on its own, doing its own thing and I haven't really been following it that much. But anyway, function overloading is using the same function name with different arguments. And they're really different functions. What the C++ compiler does is the compiler's name for that function is the function name concatenated with each of its types in the sequence they occur in the calling arguments. Angled name. So an overloaded function is just a separate function. It's a separate name for the compiler, treated like any other function. But semantically, for a designer, it's very useful because we say print function. 1 argument, 2 arguments, 10 arguments. They're all doing this operation print. So conceptually, it helps us understand, yeah, this overloaded function. It's doing the same thing, it just needs some different arguments in this case. It is useful. It's added classes. We've already talked about that a little bit. And the purpose of a class, typically when we design a class, we have some data, some state, synonyms, data that the class holds, and the class's job is to manage that data. So we turn over all management of that data to the class, and then any other program that wants to use it simply interacts with our class in a very simple way. And it does two things. One is that it ensures that the data stays in a valid state. And another important thing is that we can make the access much simpler because the user doesn't have to understand the design. It might be a very complicated data structure that takes a lot of detailed knowledge to correctly manipulate. But we can hide all that in a class, let the class do all that. So the class may have some private functions that it takes a lot of design knowledge to know how to call them correctly, but the public-facing, public member functions are all simple. You shouldn't have any design, you shouldn't need any design knowledge to use. One of your goals in designing a class is that a user can use your class without understanding how it's designed in terms. You know, that's a goal. We can't always achieve that perfectly, but we work really hard to try to do that. C++ added scope-based resource management. This very elegant management of resources. That's really important. Wei-Heng and Nog and I are all writing code for the same process. We're colleagues sitting in adjacent cubicles at work, and we're all writing code for the same process. I don't own the files that I use. I'm sharing them with Wei-Heng and Nog. The compiler, when it creates a process, will only allow us to define 20 file references. By default, that's what a process is. I think it's 20. And so if I use 17 and I don't close them, Nog and Wei-Heng only have 3. So we don't own the design of the class, so the user doesn't own those resources. They're sharing them. Sharing names, sharing files, sharing database readers, you know, blah, 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 blah. So this scope-based resource management means that a user of my class, if my class opens 3 files, as soon as that object goes out of scope, bam, those files are closed. Really important. Supports professional development. If you don't develop understanding that you are sharing, you're not a professional developer. Inheritance. So C++ adds inheritance. So inheritance is we get inheritance when we have a base class, and from the base class we derive specialized classes from it. And it's a particular syntax. It's simple, easy to do. We'll talk about, not today, but some other time. And what happens with inheritance is that any member functions of the base class that are implemented are shared by every derived class. And so we have this nice code sharing. Without inheritance, we'd have to write that same function in all those derived classes. And we used to think that was that was why inheritance was important, and that was dead wrong. Why it's important is a thing called substitution. The language guarantees me, and not just C++, C#, all the object-oriented languages guarantee you that if a function accepts a pointer or reference to a base class, it will also accept a pointer or reference to a derived class. So I can write a function. I have a silly little example on inheritance hierarchy of soldiers. There's a soldier class, and a private class, and a corporal class, and a sergeant class, and a captain, and a major, and whatever, general. And they all salute. And a private, yes sir, salutes very crisply. And a general, as you were a private, can be very casual. So they have slightly different behaviors. They all salute, but they have different behaviors. I can write a function that accepts a soldier pointer or reference, and it will salute depending on whatever object, the type of the object I passed it. If I pass it a private, that salute in the function will get a private salute. If I pass it a general, it'll get a general salute. So that substitution is a very powerful way for writing flexible code. And that is the importance of inheritance. Code sharing is just a nice added benefit. Substitution is the real issue. Templates. So we already mentioned templates allow us to write once a class that has to be instantiated for a bunch of different types. If it's a container, I don't want to write the same container code for ints and write it for doubles and write it for complex. Just write it once. Now, the compiler, with templates, what's really going on is the compiler is writing those classes. Those separate classes exist. If I write a container C of int, C of t, then if I instantiate with C of int and C of double, there's two classes. The compiler will generate a C of int and a C of double. But I don't have to. And there's a nice bunch of template containers. Streams are another nice facility. So most all languages, C#, Java, Pascal, C, all use function-oriented I/O. Scanf, printf, blah, 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 blah. C#, C++ has this really nice, flexible stream-oriented I/O. So, for example, anything that's declared as an O stream accepts output, and a cout is a standard O stream that connects your program to the console, and I can insert a whole bunch of stuff into that. I don't have to make separate function calls. I can insert into cout, insert this double, insert a string, insert a widget, whatever. And we'll use that a lot to do some very interesting flexible stuff. The other thing is that in the prototype code that I generated, I have some display functions that accept an O stream called out. And by default equals standard cout. By default, I bind that to standard cout. And so if you just use the display function without naming a stream, it'll write to cout. But if you name a file stream, it'll write to the file. If you name a string stream, it'll write to that string. Show me how you do that with printf and scanf. Ain't gonna do it. Show me how you do that with console.write. Ain't gonna do it. Okay. So. There are similarities between C and C++. They share the same compilation model. I'm going to talk about that in a minute, so I won't click on that here. Also because I'm accidentally linking to an old slide. I did a bunch of changing of the slides this weekend, and I didn't get all the links right. You'll discover that I've got so many links here, I'm in link hell. Okay, so over time, if you're kind and you say, send me an email and say, Dr. Fawcett, on lecture 3, in the middle of the page, there's a link to that's wrong, then I can fix it. But a lot of times I get an email from somebody saying, you got a bad link. Okay, I have about 300 pages in his website and typically about 30 links per page, you gotta be more specific. But anyway, so scopes, let's talk a little bit about scopes. So scopes come in two flavors. There are compile time scopes and runtime scopes. So namespaces, classes, enums are an interface, which I'll qualify in a minute. They are compile time scopes. Did I say this already? So maybe I did. I'm an old guy, I forget what I said. So, but compile time scopes are there to control how your code is laid out and what can access what else. But when the compilation is done, they're gone. They don't exist anymore. Runtime scopes exist at runtime. And the runtime scopes are the functions and controls. Functions and controls are the guys that when you enter their scope, they allocate some memory and store stuff, and then they're deallocated when you go out of scope. That's true of functions and controls. And anonymous scopes. In my code, if I do, with no name, just empty brace, memory is allocated there, and occasionally we'll use that to do stuff. But for the namespaces, classes and structs, enums, and interfaces, those are compile time only artifacts. Now, C++ doesn't have an interface construct, unlike C# and Java. But in C++, classes and structs are identical, except that structs are by default provide public access and classes by default provide private access. And you can change that with access qualifiers, public and private and so on. Okay. But by default, so and a C++ interface is just a struct that has no constructors, it has a virtual destructor, and it has function declarations that are not implemented. And there's a particular way to do it. We call them pure virtual functions. You assign =0 to them. And that's telling the compiler this struct doesn't define those functions. A struct, just like a class, you can have constructors and destructors and all that kind of stuff. But for an interface, we make it with a struct and function declarations, and the only implementation is a virtual destructor with an empty body. And I'm not going to tell you why this morning. That'll come, but it'll take us a while to get to it. So these are include relationships. So a namespace can only include everything, but can be included only by another namespace. Classes and structs can be included by almost everybody and can include almost everybody. So I can't define a namespace inside a class, but I can define another class inside a class. I can have nested classes. We don't typically use that in C++ because there isn't quite as much need in Java for syntactic reasons, but you can do it. And you can define an interface in a function if you want to, and so on. We can define an interface or a class inside a control if you wanted to. We typically don't, but you could. Syntactically, you can. So what's this namespace all about? So a namespace is just a name extension. And the idea is this. So this time, Nog is going to work on a different team, not on my team. He's working on the display team. And I'm working on the signal processor team. And his team has defined a class called widget. And my team has defined a class called widget, and they're totally different classes doing totally different things, totally different interfaces. How does the compiler distinguish them? We use namespaces, so Nog, who works on the display team, will wrap all his code in a display namespace display, and so we can access that as display : widget. And my team, the signal processing team, will wrap our code in signal processor, namespace signal processor, and will access my widget with signal processor : widget. And if I'm not compiling with the display code, I don't have to qualify it with a signal processor : I only have to qualify it when it's ambiguous. Cool. So the differences I describe here in a little more detail, these differences. I've already at the top, I summarized them, but there's some words here, about it. Talks about the C++ resource management, talks about value types, types that can be copied and assigned. And all of this, I think this is a nice summary and a C++ language comparison. I don't think I put that in the notes section. Oh, I did. It's in the notes section. So if you go to notes, C versus C++, that gets to this page. So wouldn't be a bad idea to go back and read, that stuff down to the bottom. Now you got the rough idea, go back and read it, Will you know everything about it? No. The detail will be coming out over the course of the semester, but you have a really good mental model. And that's what we're after this morning, is to start setting up that mental model. Okay. C++ and assessment. So C++ is very powerful. We can program at a low level of abstraction. We can write device drivers. We can talk to devices. We can access memory directly. We can access the API of any platform we're on. Some code that you will use, some of my code, I've written a file system set of packages that you'll use in your projects that I programmed from the Windows API. I have a corresponding one for Linux that I programmed from the Linux API. So, has direct access to memory. User-defined objects are first-class citizens. They can live anywhere, not just on a managed heap. They can live in stack memory, static memory, heap memory, and that affects their lifetimes. So we'll talk about that a little more in a minute. Supports structured design, object-oriented design, generic design, flexible memory model. Language emphasizes performance. You don't pay for features you don't use. That's really nice. C++, you can write fast code. That's one of the reasons that the Java JVM was written in C++. And the C# CLR was written in C++. Not the only reason. Because Java and C# can't do some of the things you got to do. They can do it indirectly in a very clumsy, awkward way that no designer would ever want to do. Almost no runtime checking, but you can provide it if you want to. Platform agnostic. C++ you'll find in almost every platform, even the little RTOSs, the real-time operating systems that run on devices and stuff. Most of them, not all of them, most of them have C++ compilers for them. And has a governing standard, C++ 11, 14, 17, these are coming. Visual Studio 2017 has implemented most of C++ 11, a little bit of 14, not all of it, and not too much of 17, but all that's coming and will come with updates to the Visual Studio. C++ has a lot of useful features. Callable objects are things like functions, but some of them are more powerful. A function is a callable object. Anything that you can invoke by naming, passing in arguments, or just using empty parens or whatever. There's a class type called a functor that implements operator paren, and so instances of that class you can invoke with the parens. And it turns out that's more powerful than just invoking a function for reasons we'll talk about, in a couple of weeks, not immediately. And there are lambdas, which are anonymous functions you can define anywhere on the fly and invoke. And so I can write a function, a template function, that will accept any callable object, and it turns out it's a really nice way to make very flexible code. I could have used lambdas, for example, in the prototype code that I've given you for the database. I chose not to because I didn't want to overwhelm you with all the tricks and techniques and gadgets and stuff. I was trying to keep it simple, fairly simple, not too simple, but fairly simple. So, but we'll talk about that. Templates support specialization. C# and Java generics do not. C# and Java generics are runtime artifacts. The generic container, for example, is really a container for objects, and the type is casted in and out of the container. It's really what happens at runtime. There's casting going on, essentially the casting operation. Really containers of objects. In C++, that's not what happens. Those are all bound and resolved and bound at compile time. And because it's bound at compile time, we can specialize it and say, compiler, in this case, don't use that generic template, use this specialization. C# and Java do not have specialization. So it makes it easier to write generic things with C++ using templates because you have specialization. And we'll see, all of this is coming. We're just setting the mental model now, you'll see it all. Deterministic resource management, allocate resources in constructors and other member functions of the class. Always return them in the destructor, happens automatically. Users don't have to interact with that in any way. Java and C# obviously have a way of allocating and returning resources, but in the managed language, Java and C#, that's not scope-based. It's done by the garbage collector. And what happens is the garbage collectors they're very well engineered things, they work pretty well, but there's no guarantee an object, if it sits around long enough, garbage collectors are tiered, and that object can migrate up to higher level tiers, and if it's in a higher level tier, it may never get collected. It's up to the implementation of the compiler. It may say, we got enough memory, we don't need to reclaim that memory, I'm not gonna collect it. I'm not gonna burn up the CPU cycles to collect it. But suppose that object is holding a database lock, a reader. It's open. Nobody else can access that record, ever. Databases, a good database will, if something has been locked for more than 20 minutes, will free the lock. But and so that's deadly. Not good. Now, the Java and C# guys are, yeah, but you can write dispose. You can write dispose. And what dispose does is give you the opportunity for the user to call dispose, and all those things like database locks and readers and whatever are returned. The memory isn't returned, but everything else you can return those resources. The only problem is that every single user of your class has to remember to call dispose. C++, nobody has to remember anything except the designer. The one person, the designer, has to do it right. And when it goes out of scope, everything's returned. Guaranteed, not everybody's going to remember to call dispose. I write lots of C# code, and there's lots of disposable objects I use, and I don't remember to call dispose on many of them. And lots of other professional, I've seen lots of professional code. Same thing, they don't remember. So this scope-based resource management is very elegant, works beautifully. Why C# and Java didn't adopt it is totally beyond me. I think garbage collection is the solution looking for a problem. Forgive me if I repeat myself. I do that a lot. I'm an old guy. So. Okay, has a very rich library ecosystem, you know, blah, 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 lots of nice stuff. It's very expressive. Namespaces and type aliases allow you to endow your code with semantic meaning. I have done that in the prototype for Project One. And we'll talk about that. I can talk about it a little bit tomorrow, but mainly we'll talk about it on Tuesday. And I'll walk through it in some detail and try to show you, what that means. Your goal is to write code so that the reader understands exactly what it's trying to do. And C++, I think, allows you to do that a little better than any of the other languages. They all can do it. But I like the way C++ does it a little better. Operators help you code algorithms with syntax close to what you use in the way you describe them on paper. So all my degrees are electrical engineering. I'm not a computer engineer, even though I teach all computer engineering courses. I'm an EE to my core. I used to design control systems, and I worked on radar systems, and a lot of it was algorithmic stuff. And I did, so when I was designing control systems, I started out writing a lot of design code in C. It was very hard to get those algorithms correct because the code implementation didn't look anything like what I wrote on paper. But with C++, when I moved to C++, the operator symbolism allowed me to write algorithms in a way very close to, using good naming, very close to the way I write them on paper. It made it debugging those algorithms and understanding, visualizing them, understanding what they were doing much easier. Binding lambdas to standard function allows you to provide locally named blocks of processing you can use in many places in your program. You probably don't really understand what that means, but you will. Very, very quickly we'll get to talk about lambdas. So C++ strength is widely used for system programming, application programming, scientific programming, especially where speed is needed. Weaknesses. C++ is a complex language. It is. One of the things that makes it complex is that it's big. Another thing that makes it complex is that it's context dependent. Now, every powerful language is context dependent. C# and Java are, but C++ is more context dependent than most languages. The keyword static has 4 different meanings depending on the context. The keyword virtual has 2 very different meanings depending on the context. That makes it harder to learn. Now, after a while, oh yeah, piece of cake, but it takes a while. It has some rules not enforced by the compiler. There's times when you should always use a virtual destructor. It's not enforced by the compiler. You should use initializers and constructors. You don't know what that means yet, probably, but you will. I promise you, you will. Don't return references to temporaries. The compiler doesn't enforce that. Some rules have exceptions. Compiler will automatically generate constructors. All constructors? No. Which constructors? That depends on the context. Okay. So, in fact, the language implies many implicit operations. The good news is that C++ does a lot of things for you. The bad news is that C++ does a lot of things for you. Okay. Safety is not automatic. No bounds checking. Direct access to memory can break this type system with cast. Thrown exceptions can leave the program in an undefined state, but you're in complete control. And well-designed code can be very safe. It's my job to show you how to do that. And that's going to begin on lecture 4. I'm going to show you exactly how to do that. In lecture 4, we're going to talk about what I call abstract data types, which are really just value types, types that can be copied and assigned. And we're going to take a whole bunch of functions from a class, and I'll show you how you declare it in the class header, in the class declaration, how you implement it in the CPP file, and how an application invokes it. Declaration, definition, invocation, function by function by function by function. When you're done with that, you've got the basics. Got more than the basics. You can create smart, safe pointers if you want. C++ library has already done that. You can safely cast and write exception-safe code. You just have to know how. That's why you're here. That's why we're here. So some things have been omitted from C++. No directory services. We can open a file or close a file that we know about, but we can't go to a directory and say, what files have you got? So, but you can implement those. I wrote a file system class, a set of classes, a file system package that is modeled after the .NET system.io, which I like a lot. I stole the design because it's a good design. And you'll use that in your projects. There is a directory package coming in probably in C++ 17. And I don't like it nearly as well as my own class. The problem with it is that it uses something called iterators, and there's 2 levels of stuff in a directory. There's directories and there's files, and the iteration now becomes messy and ugly. So I want to be able to say, at this path, give me the files. Get directories. So anyway, graphical user interfaces, C++. Windows supports creating instances of GUIs by default. The operating system knows how to do that. None of the other operating systems do. All the other ones depend on a packet, a module that understands, a framework that understands how to do that. Windows does it in the cover, but C++ doesn't have a good mechanism for doing user interfaces. There is something called the Microsoft Foundation classes. There's in Linux, there's Qt and KDE and WX blocks and a whole bunch of funky, old-fashioned, hard to use stuff that I don't want to deal with. Okay. So Windows Presentation Foundation, which is supported by C#, does a beautiful job. And what we will do in this class when we build GUIs is we will build them in C# using WPF, and then we will bind them to our C++ code. And that's quite easy to do. I'm going to show you how to do it. Java has JavaFX. I haven't used JavaFX, but I understand it's kind of a modern facility, something like WPF. So. No network programming, internet programming, database operations. So I've got a sockets class that we'll use in Project 3. You can write all this stuff. Database operations. There's no database. We're building one. Project 1. We're building a database. Just as good as SQL Server. Different goals. But we can persist. We can query. We can write. I'm not gonna tell you how. It's for you to design, but we can build a query language for it. Now, I'll drop a few hints, but I won't tell you how I would do it. I'll drop a few hints. So we can provide all those things. Hey, the world is ours. C# makes using the Windows API really easy. They have a wonderful ecosystem for managing the Windows platform. far more extensive than C++'s libraries. Java, on the other hand, has some facilities. They don't support the Windows platform nearly as well as C# does, but they support all platforms in a nice uniform way, and they give you a lot of support. And there's a lot of interesting stuff happening in the open source Java community. Lots of interesting stuff. So, I like Java, I like C#, but far and away, I would choose to use C++. I would. Okay. So a bunch of resources to help you, blah, 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 blah. I haven't, the department still hasn't told me who my TAs are. I think I know. The only real question is, how many of my list am I going to get? Okay. And the answer is almost certainly not enough. What that means is that you will be, I think I mentioned this last time, you will be obligated to demonstrate that you meet the requirements of your projects in a very clear way. And I've shown you in the prototype exactly how to do that. So I think this weekend you should pull down that prototype and look at it and start thinking about it and say, make up a little list. Here's what I don't understand about this. What's going on at line 43 and BB Core, blah, blah, blah. Start looking at it. We'll talk about it in class on Tuesday. Okay. So now I want to talk about some models. These are important. Let's start out with a compilation model. Can you see this in the back row? No?
Very clear.
Not big enough? Better? You can't see the whole picture here, unfortunately. So here's the way compilation works, and it's important for you to understand the compilation model. It's different than Java and C#. So in C++, each CPP file is called a compilation unit. That's what's compiled. And what happens is a preprocessor runs, and any place that the CPP file includes a header file, the preprocessor puts all of the code from the header file in place, bam, in that CPP file. So if I call in system.io, all that system.io code right there. So this turns out to be pretty big. The compiler by default doesn't show it to you. You can ask it to. There's settings that you can tell it, I want to see that. But you really don't want to see it because it's got a huge amount of stuff in it. But anyway, so so typically a well-designed package in C++ has two files, a header file and an implementation file. But it then uses a whole bunch of other header files, services it wants to use of other packages, both the system packages and other packages you wrote and the package that somebody else wrote. So you'll have one CPP, each compilation is one CPP file, and that type information is not carried over to the next compilation. That's different than C# and Java. C# and Java, compilation is based on when you use a service of another object, it goes to the metadata in that object, no header files. So it has that memory. It's building up this memory of types as it's going, and so it carries from CS file to CS file to CS file, or Java file to Java file to Java. That type information is carried over during that compilation. That's not done in C++. C++, that type of information is recreated for each CPP file. And the reason for that is that C++ was designed to support very big systems. So big that you couldn't contain in one build. You would overflow all the compiler tables if you tried to remember all that stuff. So, things are a little different this day. When I can buy a machine that has 32 gigs of random access memory, that might not be so important, but it was important when the language. But anyway, that's the way it works. So I have this intermediate file, and that's what the compiler digests. So then the compiler builds an OBJ file, an object file, that is the binary code. It's not byte code. It won't be JITted. It's the code that's going to run natively in your machine. And if I have 3 CPP files in my application, then there's going to be 3 OBJ files. And it's the job of the linker to bind those together. So what happens is, in my CPP file, if I make a call to another function in that same CPP file, the compiler just supplies an address. Bang, it's done. But if I make a call to some other package, the compiler isn't defined, doesn't remember what happened with that other package. It doesn't know where that is. And so it puts an unresolved reference away for later on putting an address. It's a hook to put an address in there later on. So every time I make a call outside this package, no address yet, just a hook to put one. And that's the job of the linker, to resolve all those unresolved references. All the references between packages get resolved. And so when we're done linking, and by the way, we may have a static library here that we don't keep compiling again and again because it's either system code or our production code. We're from our company that we use all the time. We'll have a static library so we don't have to keep building it, and the linker will bind all of that together by resolving those references into an execution image. But the story isn't quite over yet, because I may have some dynamic link libraries that are not part of that image that are loaded by the loader at runtime. So when my program starts up, the loader pulls up this image and gets it running with the help of the operating system. But when the program makes a call into some function in the dynamic link library, at that time the loader loads it. It's a lazy loading. So, so this is the way compilation works, and this results in a running process. That's the way it works. And when you look at templates, one of the things you'll see is that all of the definitions of the member functions of a template are in the header file. Every template function has to be in the header file. And the reason for that is the compiler can't generate code for that template until it knows what T is, what the template argument is. You can't lay out code unless you know the size of the objects you got to lay out. So when you compile a template, it's just basic syntax checking happens. No OBJ file is generated. When an application specifies, I want widget of int, now the compiler can lay it out, and it does, but it can only lay it out if it's got all the definition, and the only place it's going to get a definition is from a header file. Thou shalt not ever include a CPP file, ever. It does nasty things to the build process. Okay. And if you don't, you probably won't remember that. But when we get to templates, I'll talk about it again, and you'll hear about that again. All right, that's the compilation model. There's more models. Computation model. So in the computation model, here's our program. And our program has, these are stack frames. Remember I told you the stack frame was the memory that was allocated, the Scratchpad memory that was allocated when we entered a scope. So when we enter main, this stack frame is allocated, then main calls a function, and we generate a stack frame, and that function calls a function, generate a stack frame, that function calls a function, that function calls a function, and here we are with a you know, our mental model is an array of these stack frames. The compiler may not lay them out that way. When we have multiple threads, it doesn't get laid out that way. But that's a decent working model, just a good mental model for it. And the memory in our program comes in these static memory, stack memory, heap memory flavors, and we'll talk about them in just a minute. And the program has access to a command line. Even if it's a GUI, it has access to a command line. CIN is a C++ stream input. A standard in is a C-style input, and you're not allowed to use standard in. The program works just fine, but I want you to learn to use the libraries. So, files. So this reads stuff from the keyboard. This reads stuff from a file, and there will be a corresponding OS stream writes to a file. Cout is writing to the terminal, and there's error logs and stuff like that. So this is the computation model. Now there's a memory model. So we have static memory, and so it comes in 3 blocks. So the static memory block has the lifetime of the program. A lot of this is allocated laid out by the compiler. Some parts of it are initialized at runtime. Some parts of it are initialized by the compiler. Some parts are initialized. If I declare a static local variable in a class, that resides here. Static, there's only one of those. No matter if I have 15 or 32 or 1 instances of that class, no matter how many I have, there's only one place that data is stored, meaning that classes share all their local data. All their static data. So if I make a static data a member item of a class, that's shared among every instance of the class. So static memory has a lifetime of the program. Doesn't ever become invalid because some other memory writes over it. Nothing will ever overwrite that while this process is running. Stack memory is temporary memory used for runtime scopes, and this is the lifetime of the validity of this memory. The memory is valid during from the time that scope was declared, from the time a variable is declared in that scope, it's valid until it leaves the scope. So that memory is valid from the time that scope is entered until the time the scope is left. And immediately after that, it becomes invalid. Doesn't mean it goes away. It just means that some other scope can overwrite. And it's not just function scopes, you know, an if block and a for loop, they do the same thing. Heap memory is where things are stored at the discretion of the designer. The designer calls new, it gets allocated in the heap memory, and when the designer writes code that calls delete, that memory is returned to the free memory list. So those models, the compilation model, the computation model, and the memory model are things it has to be second nature. You have to really understand, yes, I got it. You don't even think about it. You know it so well, you don't even have to think about it. That's what you need. Okay. Good. We will be talking, you're invited to click on some of these. I have mentioned a couple of times as I'm clicking around that there's some of these links go to old files. I will fix those this weekend. If I have the energy, usually by the end of the day, I'm wiped out. Okay, but if I have the energy, I'll fix them tonight. So, Nag's going to send me an email and, natter at me. But for sure, I may fix a lot of these links today if I have the time. If I don't have a constant stream of students. But anyway, they'll get fixed real soon so that, by Sunday for sure, everything should be fixed, pointing to all the new stuff, the stuff I want you to see. And I think you should go click around and, use that to help yourself get oriented to the language. Classes and object relationships are important. Oops. Classes and class relationships are important. There's only 4. Inheritance, composition, aggregation, and using. And they're completely illustrated with this. It's going to require a little bit of conversation on our part to make this clear to you. There's only 4 relations, and that's all that's needed. All that's needed. Surprising that those 4 relationships are enough to do anything you need to do with software. There is a object model that you'll need to understand, and I'm going to spend probably Monday or Tuesday. We'll talk about this slide a little bit. There are I've got a base class that composes a C object and is inherited by D. Composition means that C is contained totally inside B, and derivation means that B is contained totally inside D. Don't worry about that now. We will go over that really carefully, and I've got code. I will run code that will prove to you that this is correct. This is exactly what happens. And it turns out that's important. It's important that when you understand this, you understand why the compiler is generating, how it's handling constructors and what constructors are doing. What this guarantees is that when D is constructed, the language guarantees that a B constructor is called, and when B constructor is called, the language guarantees that a C constructor will be called. Because they're inside each other. It's part of, and so I can't effectively construct D without constructing all those. So the language guarantees that when those relationships hold, those constructors will be called, and the destructors are called correspondingly in the reverse order. So, lots of stuff that the language, the way the language behaves, it depends on these fairly simple models. And I don't know why, Strauss Strip doesn't tell you that. He tells you that, but he doesn't show you a picture. And the text we used last year, which I don't like as well, doesn't show you the picture. Nobody does. So you got the picture. All righty, with that, I'm going to stop. So, help session tomorrow morning, starting at 9 o'clock. If there aren't any seats available, I won't let you in, but I will do a second wave at 10:30. I'll kick everybody out at 10:30 and accept the second wave. But don't decide to come at 10:30, because if there is an overflow, there won't be a second session. Come at 9, and if it's full, then go down on the 3rd floor, one of the lounge areas, and work on Project 1 or read Strauss Strip or whatever. Best, pull down the NoSQL code, look at it. See you then. I'll see you on Friday, or I'll see you on Tuesday, whichever comes first for you.
打20盘了，还是看第一节，真该删了已经，完全打不开去了。我现在上的不高，我但是我打不到位，没有，我排不到位置。一直数据多出来。之前的那个也有关系，所有的我现在 KDA 是3.8，我重新申一个，真觉得得重新申一号2分的话。在练了，我是说这边老哥有没有在练的手法？我那个被我们打爆了。 对线能力很强，但是对抗就是他因为他都是台湾，他队友就比较强，队友就